Okay, we're going to talk about combinations of capacitors, and we're actually going to, for the first time, we're going to talk about an electric circuit. And you guys have heard of circuits before, electric circuits. Now, these are pretty boring circuits in that there's no current flowing in our circuits. We're going to get to current here pretty soon, but we're going to be looking at a whole bunch of capacitors hooked up together that are all in electrostatic conditions. We're going to look at them once current has stopped flowing and everything is static, electrostatic condition. So, but first, we'll review capacitance. We'll talk about circuits and some of the symbols we're going to use to represent things that are in a circuit. I'm going to give you something. This is not in the book, but I think it's a very useful concept. It's called the voltage walk, and this is when Voltage Man makes his first appearance. Okay, and then we'll talk about capacitors that are in parallel and capacitors that are in series. Okay. So first of all, what is a capacitor? A capacitor is any arrangement of charge separation. Anything can be a capacitor. If you've separated charge, you have sort of a capacitor. And we said so this is our review of capacitance. You know, if I've got a blob of charge over here and a blob of charge over here, and this is positive and this is negative. Now, the amount of positive and negative charge are equal. In a capacitor, capacitors, or things that have capacitance, are systems where there is no net charge, but you do have charge separation. So you have as much positive charge over here as you have negative charge over here. And so we're going to call this Q, and this, of course, has negative Q. And then we measure how much work per unit charge we have to do to move a little test charge from the negative to the positive plate. How much work does it take to do that? Well, that's per unit charge, and that's a change in voltage. And all we do is we say the capacitance, by definition, is the amount of charge on this plate, or on this object here, divided by that change in voltage from the negative to the positive plate. A capacitance is always positive, okay? So think of this as being the positive charge and the positive voltage going from here to here to figure it out. Now, we figured out that the capacitance of just a sphere, right? If you just have a sphere with charge on it, and you say, okay, the negative charge is infinitely far away, we said that the capacitance of that was equal to 4 pi epsilon naught times R. And we derived this last time, so if you don't remember, look it up. But we got this by just dividing the charge on this sphere by the voltage to go from the negative charge, which was infinitely far away, and we put it, brought it in here and measured how much work per unit charge that took, the voltage, and we divided it, and we got an expression for it, and things canceled out, and we ended up with this. Now, if you have a parallel plate capacitor, two parallel plates, and you hook them up to a voltage source of some kind, like a battery. Here's my battery. Here's my terminals on my battery. These are just two parallel plates with empty space in between it, and we force charge to be on this plate, and an equal amount of negative charge will be on this other plate. And we found that, and this was a little bit more involved, this derivation. We had to make 2 or 3 different substitutions. But what you end up with is a constant of nature, epsilon naught. And the greater the area on the plates, the greater the amount of charge you get for the same voltage across the plates, divided by the distance between the plates. D is the distance separating these plates. And so what we see here is that capacitance for these two systems depends on basically the essential geometry of the objects and constants of nature. Okay, so so that's what we did last time. Okay, now what we're going to do is we're going to actually place this capacitor, or these, and we usually the capacitors we're going to use are parallel plate capacitors in a circuit. Now, by the way, if I know you probably haven't got to it yet, okay, but in the last assignment, the example problems was to determine the capacitance due to a cylinder. If you have a core of a cylinder that's positively charged and the outside is negatively charged. So it's go through those, because each arrangement of charge separation will have a different equation for its capacitance. But this is the most common one. This one you really should memorize. Okay, because most capacitors that we're going to deal with are going to end up being parallel plate capacitors. Now, I sort of have it drawn in a circuit right here. So let's talk about circuits. A circuit in electricity and magnetism. A circuit is a closed, no, it's a closed circuit. It's a open or closed, it's a conducting path. Okay, it's where you have some conducting material in some kind of a loop. Yes? Oh, thank you. And of course, if you took a little, like a C battery, which would look like that, and you taped a wire to it, and you put a little Christmas tree light bulb on here, that's a circuit. Okay, so here's my Christmas tree light bulb, and if you connect these wires, it's going to give off light. Now this is actually a conductor. This is a circuit, that has a current running through it. And that'll work. Or, you can take that same, C battery and put a wire to it, and then have a little aluminum foil, flattened out like this, and you take another sheet of aluminum foil, and you make a little flat plate like that, and then you have a wire, and you attach that to a battery, and that's a circuit as well. Of course, current doesn't flow in this one because the electrons can't jump across that gap. But this is a path. So you can think of this as a path where you can get back to where you started. So let's say I've got a little person here, and we're going to call this is voltage man. Now, voltage man really only has one superpower. He or she, I don't know. I'm sure there's voltage women out there. Huh? There are voltage women out there. Yeah, of course. There's voltage. I don't know. There's a lot of different voltage people. I'm voltage person. All right. And the superpower that a voltage man would have is that they can go around a circuit and measure the voltage instantaneously everywhere. So essentially, they can exceed the speed of light. They can be in multiple places at once. And what they do is they walk around a circuit and they measure voltage. And if you have something where voltage man can start here and go around and come back where they came from, that is a circuit. See, this is a circuit because you can start here and walk around and get back to where you started. That's a circuit. Here's something that is not a circuit. That's not a circuit because if voltage man starts here and walks, can't get back to where you started. Okay, so it's not a circuit. Okay, now this is called a closed circuit, what I have here, because you don't have to jump across any gaps. You just go around and you get back to where you started. Here, you got to jump across this empty space here to continue your. So this is called an open circuit. And in an open circuit, current can't flow. The electrons that flow in a wire get stuck, and they get trapped right here, and so everything stops. Okay, now this is kind of awkward, drawing light bulbs and batteries and things like that. So we have certain symbols that we're going to use that are going to make, this practical. Let's talk about the battery, and we're going to talk about batteries in more detail later on. But batteries are often called voltage sources and or voltaic piles. That's a very archaic name for them. But there's chemical potential energy stored in the way they're arranged. And I think in some of you who took AP Chem, you may have done some electrochemistry, and you may have studied how these chemicals actually store energy and provide a voltage. But we're not going to deal with that here. We're just going to treat them as things that, okay, instead of drawing a C battery, we're going to do this. So if you see this symbol drawn, where this is usually, this is shorter and thicker, and then this is kind of a skinnier line but wider. This is the symbol for a cell, an electric cell. And an electric cell, by the way, if you have more than one electric cell, you've got a battery of cells. And then a whole bunch of them, they ended up being called batteries. And now electric cells are essentially called batteries. We kind of have left that electric cell behind. But technically speaking, if you only have one of these guys, you have an electric cell. And then you put more than one together in your flashlight, you have a battery of cells. And now we just call them batteries. Now, a light bulb, we're going to get to that later. That's something that actually uses the energy that's flowing in the circuit. It's called a resistor, and we'll get to that later. This guy right here, two plates that, where positive charge piles up on one plate and negative on the other, that's a capacitor. And we have a symbol that's very simple and makes sense. Looks like that. So don't get the electric cell. This is for a capacitor. This is the symbol for a capacitor. It looks kind of like that for an electric cell, except electric cell, this is thicker and shorter, and this is, cross. These are parallel and the same length. Okay, so that's for a capacitor. Now we have one other symbol we're going to use, and that is the symbol for a switch. Now a switch is a device that allows us to open or close the circuit. And so it's a very simple thing. We just kind of draw a dot like this. A line like this. And this represents a break in the wire. And when you close the switch, you just pull this thing down, and so the wire now is connected. So this is the symbol for a switch. Okay. And so now we can put these three symbols together to form a complete circuit. So let's do that. There's my electric cell. And here's, let me put the switch up here. and then I'll put my capacitor right there. Okay. Now, here's what's going on. This is my battery, and my battery, or my electric cell, what it does, I'm just going to call them batteries, okay, but it's an electric cell. What a battery does is it boosts the voltage in the circuit. Now, if you have an electric cell like this, it's I think it's 1.5 volts. Okay, you put more of them together, you get a higher voltage. You put them in series, you could boost the voltage up. And but you can get 12-volt batteries or 6-volt batteries or whatever you want. So I'm going to call this delta V. And what this is minus and this is plus. I'm going to put a minus and plus here. And what this means is that when voltage man walks around this circuit, you're going to start here. And I always try to start my voltage walks. I'm going to go on a voltage walk. I'm going to start here and I'm going to walk around the circuit. And I'm going to start here and I go, oh, I'm going to get boosted in voltage. And then I'm going to walk around here. And then I've come to the switch. Now let's close the switch. Now what that's going to allow to happen is that current is going to flow in this wire. And it's going to force positive charge to build up on this plate until the capacitor has as much charge as you can get on it for the given voltage that's supplying that charge. Okay? And now you have to wait a little while for that to happen. Depending on what this voltage is and what this capacitance is and how much resistance there is in the circuit, we'll get to that later, it will take a little while. So what we're going to do in these problems is we're going to say we're going to close the switch and we're going to wait until there's no more current in the circuit. And we now have reestablished an electrostatic condition. That is, there's no more flow of charge. So you close this, you wait a few seconds, and then you come back, and now this is full. There's no more charge flowing in the circuit. So here's voltage man. Okay, boom! Jumps across the electric cell. I've got voltage. I've got energy. The electrons in here, they're not moving, but they contain energy per unit charge. Okay? You walk across here. Now, when you're walking across the wire, you're not changing your voltage at all. Okay? But then you get to the capacitor. And voltage man jumps down the capacitor to get back to the voltage where he started. Okay, so when you go from here to here, when you start up here and you jump down here, you lose voltage. In fact, you get back down to the voltage where you started. So let's say there's 0 volts here, and let's say that the battery gives us 12 volts. We'll use 12 volts because 12-volt batteries are very common in cars and stuff and in robots. All right. All right. So, boom, the electricity's got all this voltage. It's got energy, comes across here. Voltage man is walking around measuring voltage. That's all voltage man does, is measure voltage. Says, oh, look, I got 12 volts. I got 12 joules of energy per coulomb of charge. I got 12. I still got 12. Boom. Oh, I got 0 again. I got 0 again. I got 0 again. Boom. I got 12. I got 12. I got 12. I got 12. Boom. Oh, I got 0 again. It's not a very exciting life. All right, but here's the essence of a voltage walk. If you start at 0 and you complete your circuit, you have to end up with 0. Let's say voltage man started here. What have I got? I've got 12. Boom, I got 0. Boom, I got 12 again. So when you end up where you started, you have to end up with the voltage at the end that you started with when you complete the circuit. Okay, now it's a kind of a simple idea. If you're going on a walk, a real walk in hilly terrain, and you start someplace, and you walk up a hill, you're gaining potential energy. Divide it by your mass, you're gaining gravitational potential. And then you go down a hill and you lose it. But when you end up, let's say you go on a loop, a circuit, a complete circuit, and you end up where you started, if you end up where you started, do you have a different potential energy? No, you have the same potential energy that you had where you started, because you're back where you started. It makes sense. Okay, so this is not, spooky, black magic or anything. This is it really makes sense. Okay, so now let's take a look at this capacitor and see why it is actually a voltage drop. Let's magnify the capacitor. And what happens is this voltage, it forces positive charge to flow into it until it is as full as it can be. And what you have is an electric field inside here. And in that electric field, you've got a you've got a voltage difference from here to here. Now, think about voltage man. Voltage man holds in his hand a little test charge, okay? A little positive test charge. And he uses that little positive test charge to measure the potential wherever he is. Now, imagine a positive test charge right here and moving down like this. Do you see that it's going to lose potential as it moves with the electric field? Sure. Yeah, because, and also remember our definition for delta V is equal to E negative E dot ds. Well, here, let me zoom in because I did that way too small. So this positive charge is moving along with the magnetic field. If E dot ds is positive, then you got this negative edge, so my change in voltage will be negative. We're losing voltage. Well, we got to lose voltage because when I had 12, I started with 0, went up to 12. I got to lose 12 to get back to where I started. So now, how much charge is here? Well, this is related by the equation for capacitance. Capacitance is equal to charge over delta V. Well, we know what delta V needs to be. What does delta V need to be for my example I'm doing here? It needs to be 12 volts. Now, if you were given the capacitance and you know it's got to be 12 volts, you can solve for the charge that's stored on the positive plate. Now, we talk about capacitors storing charge. Please know this. All capacitors are electrically neutral overall. Okay? So when we say the charge on a capacitor, we're talking about how much charge there is on one plate. And we know that there's an equal but oppositely signed charge on the other plate. Okay? Yes?
Why does the capacitor wait for the charge to build up on the first charge? I'm confused as to what's going on there. So it has to wait a couple seconds or something?
Well, it takes a little bit of time. If there was no charge, now remember, these are really physical things. It's actually electrons that move in a circuit, but let's pretend that they're positive charges that are moving in a circuit. And we can thank Benjamin Franklin for that confusion. Imagine the battery is pushing positive charges. Now, positive charges repel each other, right? But they're compelled by the battery. The chemical reaction forces charge to flow. It actually creates an electric field in the conductor that forces the electrons to flow. But imagine these positive charges moving down this wire and then filling in here. Well, you have to force them together, right? They're repelling each other. And the amount of repulsion, but they're also being stuffed in there. So you kind of push them in as hard as you can. Now, if you had a battery that instead of 12 volts was 24 volts, you got a lot more push. That means you can crowd the charges more on that plate. And so you'll have twice as much charge, and you'll have twice the electric field in here. Okay, but it takes a little bit of time to do that. But don't worry about the time it takes to fill this up, because we're only going to be looking at these capacitors after they have completely filled with charge.
Okay, so
Later on, we're going to deal with capacitors that are they're called RC circuits that are dependent on time.
so if we're waiting for the capacitor to fill with charge on the positive plate, isn't the battery still flowing at that point, or is it?
Yeah, it is. I mean, current is flowing in the circuit while the capacitor is charging. But we're only going to look at the capacitor after it's finished charging.
Well, what's happening there with the battery at that point?
Oh, the battery just sits there, and it just keeps pushing charge in there. I mean, it's not adding charge in it. It's just keeping the charge from escaping. Remember, these guys, they hate each other.
Oh, does that come from the finite amount of charges in the battery, or I'm
Don't worry about that right now. Okay, just know that there's charge stuffed in here, and they want to get away from each other, but the battery keeps them there.
until it reaches the threshold where?
Yeah. Well, if you put too much charge on a capacitor, you can get a spark to jump across these plates, and that's a failed capacitor, and that's when magic smoke comes out of your circuit and bad things happen. All right. Now, so we've got two equations. Let me back out a little bit. Well, we've got this idea that the battery forces charge to fill this capacitor, and voltage man walks around, gains voltage, loses voltage. So the voltage drop here has to be equal to the voltage gain here to get back to zero. And that's really a conservation of energy idea. All right. Well, now let's talk about if I have more than one capacitor. We're going to talk about parallel capacitors. In a parallel plate capacitor, you've got two capacitors that are just like what you would think. They are parallel. So let's parallel capacitors. And let me erase this and start a little lower. Okay. So here's my battery, and then I'm going to come up here, and then I'm going to put a capacitor here. I'll call that C1, and I'll put a capacitor here. We'll call that C2. Okay, I'm sorry, I can't erase that anymore. All right, so very simple, and this is our delta V. This is our change in voltage due to this battery. Now let's suppose that this has been in place for a long time, and the capacitors are fully charged. Let's take a look at voltage man. Okay, voltage man will start here, our intrepid measurer of voltage. And he says, okay, I'm going to set my measuring device to 0. Now, let's say this is a 12-volt battery. I'm going to jump across the battery. Now my little test charge has energy. Boom. Winning. Okay, it gave me energy. All right, so now I come up here. Uh-oh. This is called a junction, and now voltage man must make a choice. Will I go this way or will I go this way? Well, voltage man will say, let's go this way. Let's come down immediately. I'm a little tired. All right, so I'm going to jump down back to 0 volts. Well, if this is, let's say this is 12 volts. If this is 12 volts, what's the voltage across this capacitor? What's from here to here? No, it's got to be 12. Because now I'm back to where I started. You see, so let's take a look right here. Everybody really focus right now, because I know I've been talking a long time. Focus right now. Everything down here is at 0 volts. Everything. Voltage man can walk through a wire and say, oh, 0 volts, 0 volts, 0 volts, 0 volts, 0 volts. Doesn't matter. It's all 0 volts down here. Now, I come up here, boom! I got 12 volts now. Everything up here is 12 volts. Everything up here is 12 volts. I mean, there's nothing there to change my voltage. There's nothing there taking energy away. That's how much energy I've got. But when I jump down here, I've got to lose 12 volts to get back to 0. Or if I jump across here, I've got to lose 12 volts. Do you see that? Okay, it's kind of abstract, but you got to follow it. So we got a really important idea here. We say that capacitors are in parallel if they have the same voltage drop. If going from here to here is the same voltage drop, they are in parallel. That kind of defines what parallel capacitors are. But we also say, flip-flop it and say capacitors in parallel have the same voltage drop. Okay? Now, let's talk about charge. So, in other words, I can say that V1 equals V2. Let's say V is the voltage drop across C1, and V, or you can call it delta V, is the voltage drop across C2. They have to be the same, because look, 12 volts, 0 volts, same drop, no matter which path voltage band takes. Now let's take a look at charge here. Let's say this battery is going to push charge through here, right? Push charge through here, and then it's going to fill this one up. 1, 2, 3, 4. But some of the charge is also going to go this way, right? 1, 2, 3. Maybe this is a smaller capacitor. It doesn't have as much charge. How much charge got pushed into these capacitors? How much total charge got pushed? Yeah. 1, 2, 3, 4, 5, 6, 7. That's the total amount of charge. Here, I'm going to take a little sheet of paper and cover this up. How much charge is in that upper part? 7, or 7 microcoulombs. Away, I can say let each little plus represent 1 microcoulomb. All right, so we got 7. So here's what we can say: the total charge stored by the positive plates in parallel plates capacitor is just the sum of the charges. In other words, the total charge Q is equal to Q1 plus Q2. Okay, now if you can see that, you're in good shape. All right, now we're going to use this idea now.
Even though we're going through 2 capacitors, we're still going through total drop of those.
Well, everything down here is at 0 volts. Everything up here is at 12 volts. So you go from here to here, it's 12 volts. From here to here, it's 12. So both capacitors have 12 volts on them.
Even though it's 12 volts of push that's being divided into 2 capacitors?
Right.
Okay.
It's the same drop. Think of it this way. If I'm standing up on top of this desk, I can jump down to the floor that way, or I can jump down to the floor that way, but it's the same drop to the floor.
Right, but you're not jumping simultaneously.
No. Well, actually voltage band can. That's his superpower. He can do things simultaneously.
Right now I'm picturing 2 people on the desk
Yeah.
that are 12 volts and then jumping off, but each of them only jumping off 6 volts each.
No, that's wrong. They drop the same amount.
Wait, so would it be 24 volts then if it's 12 volts each?
No.
Because that's where I think
No.
12 volts.
Let's say this represents, instead of 12 volts, let's say it represents 12 feet of height.
Okay.
I'm going to drop 12 feet from the top of the roof to the ground, from the top of the roof to the ground. You say, oh, this guy drops 12 feet. This guy also, they both drop 24 feet, or one of them drop. No, they don't. It doesn't add that way. They both drop 12 feet, 12
Where
volts.
I'm just getting hung up is the fact that the 12 volt battery is exerting 12 volts in both capacitors.
Yes, it does.
But even though it's being divided.
No, it's not being divided. No. Okay. Now I got limited time. I got to move on. Okay. So here's what I can do. Okay. C1 is equal to Q1 over delta V for 1. C2 is equal to Q2 over delta V for 2. So I can say that that Q1, I can do a substitution here. I can say that let's say that solve this for Q1. So Q1 is equal to, oh, thank you. So let me zoom out. Q1. Q1 is equal to C1 times delta V1, right? Plus, now what is Q2? C2 times delta V2. Now, what I want to do here is figure out what is the overall capacitance of this arrangement of two capacitors. Well, the overall capacitance, if I just say, well, C equals, Q over delta V, I can just say, oh, okay, the total charge is equal to the total capacitance divided by the total voltage. Well, what do we know is true about, this is the voltage delivered by the battery to the circuit. This is the voltage drop across the first capacitor, and this is the voltage drop across the second capacitor. What's true about those voltages? They're all the same, so what happens to them? They cancel out. And so C is equal to C1 plus C2. And if I can have multiple capacitors in parallel, they would all have the same voltage drop. So look, even if I have 33 capacitors, they would all, voltage man to get from here to here would have to drop the same amount of voltage. So they each have 12 volts across them. Cn. So this right here is called the equivalent capacitance of the circuit. If I've got multiple capacitors in parallel, what one capacitor could I replace them with? Just add the two capacitors together. Okay, so there you go. Now, we're going to do the same kind of analysis, but for capacitors in series. Okay, now in series, and this is a little bit harder to get. So I'm just going to put, here's C1, and here's C2. So let's say I close the switch and things start happening. What this delta V here, what this battery does is it forces charge to move up here and it fills up this capacitor. But remember, all this metal, these are all conducting wires and metal capacitors. It stuffs positive charge in here. Okay, well, what does that do to the other side of this plate? It draws an equal amount of negative charge here. And what you get is an electric field in here. Well, where do these negative charges come from? You had to steal it from the other plate. Let's say the wires are insignificant here. So you had to steal positive charge from these plates. An equal amount. Well, what does that do to this plate? You put a negative charge on here. Okay? So, let's take a look at this in terms of voltage. Okay? And now, and Kate, now the voltage is going to get shared. It's going to get divided. Okay? So here's voltage, man. Okay. Here's a cape. He needs a cape. All right. Now, so the voltage is going to start at 0, right? And then we're going to jump up in voltage. Now I have lots of voltage. But then I come here and I got to jump down, and I'm moving a positive test charge with the electric field. So I'm losing voltage. So boom, I'm going to lose voltage. But then I got to move against this capacitor, and I'm going to drop down this electric field. So boom, and now I'm back down to 0. So these two guys, these two capacitors, they split up the voltage. They divide it up. If I've got 12 volts here, from here to here, from the top to the bottom, I got to drop 12 volts. Well, maybe this is 8, but if this is 8 volts, what has this got to be? 4 volts. If this is 6 volts, this has got to be 6 volts. If this is 1 volt, this has to be 11 volts. They split it up. So in other words, delta V is equal to V1 plus V2. I should put deltas there, but I kind of get lazy. All right. Now, let's take a look at this in terms of charge. Let's say that this battery was able to stuff 4 units of charge on the top plate. So what do you have on the bottom plate? 4 units of negative charge. Well, what does that do to the top plate here? 4 units. 4 units. So in other words, the charge on the capacitor 1, we'll call that Q1, is going to be equal to Q2. It has to be equal. Okay, now everybody think for a second. What would happen if this capacitor had more charge on it than this capacitor? Yeah, I mean, now I'm saying, okay, this has got, let's say, so this had 5 units of positive charge. So that would draw 5 units of negative charge. But let's say I only had 4 units of positive charge here. That ain't going to happen. The charges are going to move around until this happens. Because remember, capacitors are electrically neutral. Let me finish. But now here I'll take a little piece of paper here. So I got to get the right amount here. How much how much charge is stored overall? Remember, storing charge, what we mean is how much is on the positive. Well, I'm going to cover this up. Oh, just perfect. I'm going to cover up that inside part. So from the point of view of this battery, how much positive charge is on the top and how much negative charge is on the bottom? There's still 4. So from the battery's point of view, there's only 4 units of charge stored on this top plate. And so in other words, capacitors in series have the same charge, and that amount of charge is the charge that we use for the overall capacitance of the circuit. Boom. Oops, sorry. See that?
So what's the point of having multiple in series?
Oh, we don't need to worry about the point of doing this yet. I mean, when you're an electrical engineer and you want to control the behavior of the circuit, now remember, these are real devices used in real applications. Capacitors have lots and lots of uses. Your cell phone has capacitors, your calculator has capacitors, this computer, everything has capacitors in it. Now, I'm not prepared at this time to tell you exactly what they're doing. We'll do that later. But right now, we're just kind of looking at the pure physics of this right now. We'll get to the applications in a little bit. Okay, so now what I can do is I'm going to solve the capacitance equation for voltage. So we have C equals Q over delta V. So let's solve for V. instead of delta V, I'll just call it V. So V is equal to Q over C. So let's do the substitution. Let's use this equation. Bring it down here. So delta V overall is going to be equal to the total charge divided by the overall capacitance of the circuit. That's here is this. And then V1 is going to be equal to Q1 over C1. Right, because V1 equals Q1 over C1 plus voltage number 2 is just Q2 over C2. But what's the same? What cancels out? The charge is the same for capacitors in series. So this cancels out of the equation, and you get the equation for the equivalent capacitance. It's 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2. Plus, I could put as many capacitors in series as I want. And this is the equation you use to determine the equivalent capacitance. Now remember, this answer right here, 1 over, is not the equivalent capacitance. It's 1 over the equivalent capacitance. So if you have multiple capacitors in series, you need to add the reciprocals. Just take, this one, 1 over C1 plus 1 over C2, add them together on your calculator or whatever, and then with your final answer, reciprocate your final answer to get the equivalent capacitor. So what this is right here is the one capacitor that I could replace the two of these with. Okay? Now, what we need to do now is we need to do a lot of example problems, but this video is already 47 minutes long, which I think is the longest one I've ever made. So I'm going to, let's zoom out, take a look at these, though. They have something that's kind of cool in common. And that is, in parallel plate capacitors, the voltage is the same, but the charge adds. In series capacitors in series, the voltage adds to get your total voltage, but the charge is the same. But you use the same equation, the capacitance equation here and over here, you use those to derive these. So if you ever get confused about, what is it? Is it 1 over C or is it C plus 1 plus C plus... they're pretty easy to derive if you understand the physics of it. Okay? That is all.